Water, water everywhere, but not a drop to drink. This age-old saying has never been more relevant. Sounds like a pirate's lament, right? But it's not just a tale from the high seas, it's a growing problem for our planet. Population growth and climate change are putting a huge strain on our freshwater resources. Urban areas are expanding and farmlands are drying up. Many regions face severe water scarcity, making it difficult to meet basic needs like drinking, sanitation, and agriculture. In some places, people travel miles just to collect a single bucket of water. Desalination is like a magic trick. It's the process of removing salt from seawater to create fresh water. This technology has the potential to transform lives. This technology is crucial for water-stressed countries located near oceans. Think of places like the Middle East, North Africa, and even parts of the United States where fresh water is becoming increasingly scarce. But desalination can be expensive and energy-intensive. The high costs and energy demands make it a challenging solution for many regions. That's why scientists are constantly searching for innovative solutions to improve this process and make it more accessible to everyone. They are exploring new methods and technologies to reduce costs and energy consumption. The key to this lies in enhancing a crucial component: reverse osmosis membranes. By improving these membranes, we can make desalination more efficient and affordable, bringing fresh water to those who need it most. Reverse osmosis is like pushing water uphill. Imagine a container divided by a special membrane. Salty water goes on one side, and pressure is applied to force the water molecules through the membrane. The membrane acts like a superfine filter, blocking salt and impurities, allowing only fresh water to pass through. This process is what makes desalination possible on a large scale. Reverse osmosis is currently the most widely used desalination technology because it's relatively efficient and produces high-quality fresh water. But even this amazing technology has its limitations. Let's dive into those. Remember that superfine filter, the reverse osmosis membrane? Well, it can get clogged up over time. This is called fouling, and it's a big issue. Salt and other gunk in the water stick to the membrane, making it less effective and reducing the flow of fresh water. Another challenge is membrane selectivity. We want membranes that are really good at letting water through while keeping all the bad stuff out. But sometimes, larger salt molecules or other contaminants can sneak through, affecting the quality of the fresh water. Scientists are always working to improve these membranes. They're experimenting with new materials and coatings to make them more resistant to fouling and increase their selectivity. And guess what? They're making exciting progress every single day. Section 4. A splash of innovation. Chitosan and titanium dioxide to the rescue. Let me introduce you to two superheroes in the fight for better membranes: Chitosan and titanium dioxide. These two materials are revolutionizing the way we think about water filtration. Chitosan comes from the shells of crustaceans like crabs and shrimps. It's a natural polymer that has been used for centuries in various applications. It's a natural polymer with amazing properties, including its ability to form films and its antimicrobial characteristics. Titanium dioxide is a common material found in things like sunscreen and paint. It's widely used because of its excellent UV blocking and whitening properties. It's known for its photocatalytic activity, which means it can use light to trigger chemical reactions. Scientists have discovered that by treating reverse osmosis membranes with chitosan and titanium dioxide nanoparticles, they can create a super membrane. This innovative approach enhances the membrane's performance significantly. The chitosan acts like a protective shield, preventing fouling and making the membrane more durable. This means fewer replacements and lower maintenance costs. And the titanium dioxide, when exposed to sunlight, can actually break down organic pollutants that try to stick to the membrane. This self-cleaning feature is a game changer for water purification systems. Section 5. A brighter, cleaner future: enhanced membranes for a thirstier world. These innovative modifications are a game changer for desalination. They represent a significant leap forward in our ability to provide clean water to those in need. Enhanced membranes mean less fouling, higher water flow, and improved water quality. This ensures that the water we produce is not only abundant but also safe and healthy for consumption. This translates to more efficient desalination plants, lower energy consumption, and ultimately, more affordable fresh water for everyone. The impact on both the environment and the economy is profound. For countries like Egypt, which heavily rely on the Nile River for their water needs, These advancements in desalination technology offer a lifeline. They provide a sustainable solution to a pressing problem. By tapping into the vast resources of the Mediterranean and Red Seas, Egypt can reduce its dependence on the Nile and ensure a sustainable water future for its growing population. This diversification is crucial for long-term stability. These advancements in membrane technology represent a major step forward in our fight against water scarcity. They are a testament to human ingenuity and our commitment to solving global challenges. By making desalination more efficient and affordable, we can provide clean drinking water to millions around the world and pave the way for a brighter, more sustainable future. This is a vision we can all work towards. Remember, every drop counts. Each effort we make today will help secure a better tomorrow for future generations. Welcome to another episode of the For Science Salah Lotfy channel. Today we're excited to highlight groundbreaking research that addresses one of the most critical challenges of our time: water scarcity. The research we'll discuss focuses on advanced membranes for desalination, a vital step toward providing clean water to communities worldwide. This remarkable study is titled Surface Modification of Thin Film Composite Membranes Using Gamma-irradiated Chitosan and TiO₂ for Enhanced Desalination Performance. It was published in the journal Desalination and Water Treatment, Volume 160, 2019, pages 32 to 40. Received date October 1, 2018, accepted date April 3, 2019. This pioneering research was carried out by a team of highly distinguished scientists. 1. Dr. Hani Gayed, lecturer at the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. 2. Assistant Professor Fatin Ismail Abu El Fadel, from the same department at NCRRT, Egyptian Atomic Energy Authority. 3. Professor Dr. Nabila Maziad, also from the Polymer Chemistry Department at NCRRT, Egyptian Atomic Energy Authority. 4. Professor Dr. Abdel Hamid El Assar, affiliated with the Egyptian Desalination Research Center of Excellence at the Desert Research Center in Cairo, Egypt. 5. Professor Dr. Mohammed Sabri Abdel Mottaleb from the Faculty of Science, Ain Shams University, Cairo, Egypt. This research explores the use of gamma-irradiated chitosan combined with nanoparticles of titanium dioxide to modify thin-film composite membranes. These membranes were designed to enhance the efficiency of reverse osmosis systems, critical for desalination. By applying advanced techniques such as gamma irradiation, the team successfully developed a surface modification process that improves membrane performance, including salt rejection and water permeability. Their findings have the potential to revolutionize water treatment systems, making desalination more efficient and sustainable. This study is a testament to the incredible innovation happening in Egypt's research community. A huge thanks to the team of researchers for their contribution to solving global water challenges. If you're interested in learning more about cutting-edge science, make sure to like this video, subscribe to our channel, and stay tuned for more fascinating discoveries. Thank you for watching the For Science Salah Lotfy channel. Hey there, science fans! Today we're diving into the fascinating world of desalination, a process that's becoming increasingly important in our thirsty world. As the global population grows, so does our demand for fresh water. Unfortunately, freshwater sources are limited, and in many parts of the world they're becoming increasingly scarce. This is where desalination comes in. Desalination is like a magic trick, turning salt water into fresh water that we can use for drinking, agriculture, and industry. Desalination technologies have come a long way, and one of the most promising approaches uses a special type of filter called a membrane. Imagine a very fine sieve that can separate salt from water. That's essentially what a desalination membrane does. Scientists and engineers are constantly working to improve desalination membranes, making them even more efficient and cost-effective. Stay tuned. Welcome back, science enthusiasts. In our quest to understand the magic of desalination, let's zoom in on the workhorses of this process: polymer membranes. These amazing materials have emerged as the top choice for desalination, outperforming other options like ceramic membranes. Polymers are like long chains of molecules, kind of like beads strung together. This unique structure gives them some awesome properties, making them perfect for desalination membranes. We can tweak their properties by changing the types of beads or monomers in the chain, or by adjusting how these chains are linked together. This allows us to fine-tune the membrane's permeability, selectivity, and mechanical strength to meet specific desalination requirements. Polymers are lightweight and flexible, making them easier to handle and install compared to bulky ceramic membranes. Polymers are also more cost-effective to manufacture than their ceramic counterparts. However, even these superstar materials face challenges. One major hurdle is membrane fouling, which we'll delve into in the next section. Hold on to your lab coats, science buffs, because we're about to tackle a sticky situation: membrane fouling. While polymer membranes excel in desalination, they're not immune to the challenges posed by the complex soup of substances found in seawater. Over time, organic matter, salts, and microorganisms can accumulate on the membrane surface, forming a pesky layer of gunk. This buildup, known as fouling, is a major headache in the desalination world. Fouling reduces the flow of water through the membrane, making the desalination process less efficient and more energy-intensive. To maintain performance, fouled membranes require frequent cleaning or replacement, adding to the overall cost of desalination. Organic matter, like proteins and polysaccharides, can stick to the membrane surface, creating a breeding ground for bacteria. Salts, particularly calcium sulfate, can precipitate out of the water and form hard scales on the membrane. Researchers are exploring various strategies to modify membrane surfaces, making them more resistant to fouling. One promising approach involves using natural polymers like Chitosan, which brings us to our next exciting chapter. Get ready to be amazed, science fans. We're unlocking the potential of Chitosan and titanium dioxide. These materials are set to revolutionize desalination membranes. Chitosan from crustacean shells forms a protective layer. It repels foulants, enhancing membrane performance. Titanium dioxide, a natural oxide, is photocatalytic and hydrophilic. It breaks down pollutants and attracts water. Combining them enhances anti-fouling and photocatalytic properties. Section 5. Gamma irradiation, unlocking the potential of Chitosan. Fasten your seatbelts, science buffs. We're diving into gamma irradiation, a tool to unlock Chitosan's potential for membrane modification. Gamma rays alter Chitosan's chemical structure, enhancing its properties. This process, called cross-linking, makes Chitosan more durable and resistant. It also improves Chitosan's ability to bind with TiO₂ nanoparticles. This ensures nanoparticles stay anchored, enhancing membrane performance. Next, we'll explore the experimental procedures for these modifications. Section 6. A closer look at the experimental process. Attention, science enthusiasts. It's time to put on our lab coats and delve into the exciting world of experimentation. Preparing those high-performance modified desalination membranes involves a series of carefully orchestrated steps. First, we need to prepare our Chitosan solution. We dissolve Chitosan powder in a suitable solvent like acetic acid to create a viscous liquid. Next, we add our secret ingredient, titanium dioxide nanoparticles. These tiny particles are carefully dispersed throughout the Chitosan solution, ensuring a uniform distribution. Now comes the gamma irradiation part. We expose our Chitosan titanium dioxide mixture to a controlled dose of gamma rays. This crucial step triggers the cross-linking of Chitosan chains and enhances the binding of titanium dioxide nanoparticles. Once our gamma-irradiated Chitosan titanium dioxide composite is ready, we can apply it to our desalination membranes. One common method is dip coating, where the membrane is immersed in the composite solution and then carefully withdrawn, allowing a thin, uniform layer to coat the surface. But how do we know if our modifications are successful? That's where our next exciting step comes in: characterization. Stay tuned for the results. Section 7. Analyzing success. Characterization and performance evaluation. Hold on to your test tubes, science detectives, because it's time to analyze our handiwork. We use characterization techniques to evaluate our gamma-irradiated Chitosan titanium dioxide membranes. Scanning electron microscopy, SEM, reveals the surface morphology in stunning detail. Next, Fourier transform infrared spectroscopy, FTIR, identifies chemical bonds in our membranes. Performance evaluation includes rigorous desalination tests. We measure water flux, salt rejection, and anti-fouling properties. Get ready for exciting results in the next section. Section 8. Promising results, enhanced performance and reduced fouling. Get ready to be impressed, science enthusiasts, because the results are in, and they're nothing short of remarkable. Our gamma-irradiated Chitosan titanium dioxide modified membranes have demonstrated significant performance enhancements compared to their unmodified counterparts. First and foremost, we observed a substantial increase in water flux. This means that our modified membranes allow water to flow through more easily, boosting the efficiency of the desalination process. Moreover, our modified membranes exhibited improved salt rejection, indicating their superior ability to remove salt ions from the feed water. But here's the real game changer. Our modified membranes demonstrated exceptional anti-fouling properties. They exhibited significantly reduced fouling even when challenged with high concentrations of organic matter and salts. This remarkable resistance to fouling can be attributed to the combined effects of chitosan's protective layer and titanium dioxide's photocatalytic activity, which work together to prevent the accumulation of foulants on the membrane surface. These promising results highlight the potential of gamma-irradiated Chitosan titanium dioxide modifications for enhancing the performance and longevity of desalination membranes. In the concluding section, we'll explore the broader implications of this research for the future of desalination. Section 9. The future of desalination, sustainable and efficient water treatment. As we conclude our journey into the world of desalination, one thing is clear: gamma-irradiated Chitosan titanium dioxide modified membranes hold immense promise for revolutionizing this crucial water treatment technology. The enhanced performance and reduced fouling observed in our research pave the way for more sustainable and efficient desalination processes, addressing the growing global demand for fresh water. Imagine a future where desalination plants require less energy to operate, thanks to membranes with higher water flux. Picture membranes that last longer and require less frequent cleaning or replacement, reducing the overall cost of desalination. By harnessing the power of nanotechnology and innovative materials like chitosan and titanium dioxide, we can unlock the full potential of desalination and ensure a sustainable water future for generations to come. Stay curious, stay thirsty for knowledge, and let's keep exploring the wonders of science together. Hey there, science fans. Today, we're diving into a topic that's crucial for our survival and the health of our planet. Let's talk about water, the lifeblood of our planet. It's essential for every living organism, from the tiniest microbe to the largest whale. We all need it, but clean, fresh water is getting harder to find. Climate change, pollution, and overuse are making water scarcity a growing problem worldwide. That's where desalination comes in, turning salt water into drinking water. Pretty cool, right? This technology is a game changer for many coastal regions. One of the most promising ways we desalinate water is using special filters called reverse osmosis membranes. These membranes are incredibly efficient at removing salt and other impurities. Imagine a really fine strainer that can even filter out salt molecules. It's like magic, but it's all science. These membranes are already helping us get more fresh water, but scientists are always looking for ways to make them even better. They're working on making the process more energy efficient and cost-effective, so that more people around the world can have access to clean water. With continued innovation and dedication, we can ensure a future where everyone has access to this vital resource. So, next time you take a sip of water, remember the incredible science that makes it possible. So, what are these amazing membranes made of? These membranes are crucial in various applications, especially in water purification and desalination processes. They act as barriers, allowing only certain substances to pass through while blocking others. The most common material used for these membranes is a type of plastic called polyamide. Polyamide is favored because of its excellent mechanical strength and chemical resistance, making it ideal for long-term use in harsh environments. It's durable and great at filtering out salt. This makes it perfect for desalination, where the goal is to remove salt from seawater to produce fresh, drinkable water. The durability of polyamide ensures that the membranes can withstand the high pressures involved in the filtration process. To make the membranes, we start with a thin support layer and then use a cool process called interfacial polymerization to create the super thin polyamide layer on top. This process involves a chemical reaction at the interface of two immiscible liquids, resulting in a dense, selective layer that is only a few nanometers thick. It's like building a tiny high-tech sandwich that can separate salt from water. Each layer has a specific function, working together to ensure that only pure water passes through while contaminants are left behind. This intricate structure is what makes these membranes so effective and essential in modern water treatment technologies. Now, here's where it gets really interesting. Scientists have found ways to tweak or modify these membranes to make them even more efficient. By adding special nanoparticles or using innovative coating techniques, we can improve their performance and make them last longer. Think of it like giving our water filters a turbo boost. These modifications can help the membranes reject more salt, work faster, and use less energy. Section 4. Putting membranes to the test characterization methods. Before we can use these modified membranes, we have to put them through their paces. Scientists use all sorts of high-tech tools to check how well they work. They measure how much water can pass through, how much salt they can filter out, and how resistant they are to damage. It's like a rigorous obstacle course for membranes. Section 5. The future is flowing. Performance and impact of modified membranes. In this section, we delve into the incredible advancements in membrane technology that are revolutionizing the way we approach water purification and desalination. Thanks to these amazing advancements in membrane technology, we're getting better and better at desalination. These high-tech membranes are designed to filter out even the smallest impurities, making seawater and other non-potable sources safe for consumption. This is particularly important in regions where fresh water is scarce and the demand for clean water is constantly increasing. Modified membranes are helping us produce more fresh water with less energy, which is great news for our planet and our future. By reducing the energy required for desalination, we are not only making the process more cost-effective, but also minimizing the environmental impact. This means fewer greenhouse gas emissions and a smaller carbon footprint, contributing to the fight against climate change. As we continue to innovate and improve these technologies, we can look forward to a world where clean, fresh water is more readily available for everyone. The potential applications of these advanced membranes extend beyond just desalination. They can be used in wastewater treatment, industrial processes, and even in the production of pharmaceuticals, making them a versatile tool in our quest for sustainability. Keep those science brains buzzing, and remember, every drop counts. Every innovation, every improvement in membrane technology brings us one step closer to a future where water scarcity is a thing of the past. So let's continue to support and invest in these groundbreaking technologies for a better, more sustainable world. Hey there, science fans! Welcome back to another exciting episode where we dive deep into the wonders of science and technology. Today, let's explore a fascinating technology that's helping us tackle one of the most pressing issues of our time, the global water crisis. This technology is known as reverse osmosis, or RO for short. Imagine a filter so fine it can separate salt from water. Yes, you heard that right. This tiny filter can make a huge difference in providing clean drinking water. That's the magic of reverse osmosis. But how does it work? Let's break it down. In nature, water naturally flows from a region of low salt concentration to a high salt concentration through a process called osmosis. Osmosis is a fundamental process in nature. It's how plants absorb water from the soil and how our cells maintain their balance. But what if we could reverse this process? This is where reverse osmosis comes into play. By applying pressure, we can force water to flow through a special membrane, leaving salt and other impurities behind. This process is aptly named reverse osmosis. The key to reverse osmosis is the semi-permeable membrane. This membrane has tiny pores that allow water molecules to pass through, but block larger molecules like salt and other contaminants. By applying pressure to the salty water, we can push the water molecules through the membrane, leaving the salt and impurities behind. This results in clean, drinkable water. This process is incredibly effective and can turn previously unusable water sources into safe drinking water. It's like magic, but it's all science. Reverse osmosis is a game changer for water purification. It's used in a variety of settings, from large-scale industrial applications to small residential systems. In homes, RO systems provide families with clean drinking water. In businesses, they ensure the water used in processes is free from contaminants. And in desalination plants, they turn seawater into fresh water, providing a vital resource to millions of people worldwide. But the heart of this incredible technology lies in the membrane. This tiny yet powerful component is what makes reverse osmosis possible. The membrane structure is designed to allow only water molecules to pass through, effectively filtering out impurities. The development and manufacturing of these membranes are a marvel of modern engineering. Scientists and engineers work tirelessly to improve the efficiency and durability of these membranes, ensuring they can withstand the pressures and demands of the reverse osmosis process. The membranes are made from a variety of materials, each chosen for its specific properties. Some are designed to handle high levels of salt, while others are optimized for removing specific contaminants. The versatility of these membranes makes them suitable for a wide range of applications. In large-scale water purification plants, reverse osmosis systems are used to treat vast quantities of water. These plants play a crucial role in providing clean water to cities and communities, especially in areas where freshwater resources are scarce. In residential settings, reverse osmosis systems are becoming increasingly popular. They provide families with peace of mind, knowing that the water they drink is free from harmful contaminants. Installing an RO system in your home can be a great investment in your health and well-being. Businesses also benefit from reverse osmosis technology. Whether it's in the food and beverage industry, pharmaceuticals, or manufacturing, having access to pure water is essential. RO systems ensure that the water used in these processes meets the highest standards of purity. Desalination plants are perhaps the most impressive application of reverse osmosis. These plants take seawater, which is abundant but undrinkable, and turn it into fresh, potable water. This technology is a lifeline for many coastal regions and islands where fresh water is limited. The global water crisis is a significant challenge, but technologies like reverse osmosis offer hope. By providing a reliable source of clean water, RO systems can help alleviate the pressure on our natural freshwater resources and ensure that everyone has access to safe drinking water. The future of reverse osmosis technology is bright. Researchers are continually working on new advancements to make RO systems even more efficient and accessible. From developing new membrane materials to creating more energy-efficient systems, the possibilities are endless. Imagine a world where everyone has access to clean, safe drinking water. With continued innovation and investment in technologies like reverse osmosis, this vision can become a reality. It's a small filter with a big impact, making a difference in the lives of millions. So, the next time you take a sip of clean water, remember the incredible science and technology that made it possible. Reverse osmosis is a testament to human ingenuity and our ability to solve even the most challenging problems. Thanks for joining us on this journey through the world of reverse osmosis. Stay curious and keep exploring the wonders of science. The unsung hero of the reverse osmosis process is the polyamide membrane. This remarkable material is the cornerstone of modern water filtration systems, quietly working behind the scenes to ensure that the water we drink is clean and safe. But what exactly makes this membrane so special? Let's take a closer look. This thin, film-like material acts as a selective barrier, allowing water molecules to pass through while blocking larger molecules like salt. Imagine a sieve so fine that it can separate the tiniest particles from a mixture. That's essentially what the polyamide membrane does, but on a molecular level. It's designed to let only water molecules through, while rejecting contaminants like salts, bacteria, and other impurities. Think of it like a superfine mesh that only lets the tiniest particles through. This mesh is so fine that it can filter out particles as small as 0.0001 microns. To put that into perspective, a human hair is about 50 microns in diameter. So, the polyamide membrane is filtering out particles that are 500,000 times smaller than a human hair. Polyamide membranes are the industry standard for RO because they're tough, durable, and highly effective at removing a wide range of contaminants. These membranes are used in everything from household water purifiers to large-scale industrial water treatment plants. Their durability means they can withstand the high pressures required for reverse osmosis, and their effectiveness means they can produce water that meets the highest standards of purity. But even these workhorses can benefit from a little boost. Scientists are constantly looking for ways to improve the performance of polyamide membranes. One of the most exciting areas of research is the modification of these membranes with new materials that can enhance their properties. That's where our next science superstars come in: Chitosan and titanium dioxide. Chitosan is a natural polymer derived from the shells of crustaceans like shrimp and crabs. It's known for its biocompatibility and antimicrobial properties. Titanium dioxide, on the other hand, is a well-known photocatalyst that can break down organic pollutants when exposed to light. These two materials, when added to the polyamide membrane, can enhance its performance and make it even better at producing clean water. Chitosan can improve the membrane's resistance to fouling, which is a common problem in water filtration systems. Fouling occurs when contaminants build up on the surface of the membrane, reducing its efficiency. By incorporating chitosan, the membrane becomes more resistant to this buildup, maintaining its performance over a longer period. How? Let's dive into the fascinating world of material science and find out. Titanium dioxide, when added to the membrane, can enhance its ability to break down organic pollutants. This is particularly useful in applications where the water being treated contains a high level of organic contaminants. The photocatalytic properties of titanium dioxide mean that it can use light to break down these pollutants, making the water even cleaner. By combining these two materials with the polyamide membrane, scientists are creating a new generation of water filtration systems that are more efficient and effective than ever before. The future of water filtration is bright, thanks to these innovative advancements. As we continue to develop new materials and technologies, we can look forward to even more effective and sustainable ways to ensure that everyone has access to clean, safe water. The polyamide membrane may be the workhorse of water filtration, but with the help of chitosan and titanium dioxide, it's becoming a true powerhouse. So, the next time you take a sip of water, remember the incredible science and engineering that goes into making it clean and safe. From the humble polyamide membrane to the cutting-edge materials being developed in labs around the world, every drop of water is a testament to human ingenuity and the relentless pursuit of a better future. And that's the story of the workhorse of water filtration. Stay tuned as we continue to explore the amazing world of material science and its impact on our everyday lives.
Water is essential for life. We need it for drinking, agriculture, and industry. But clean water is becoming increasingly scarce. Population growth and climate change are putting a strain on our water resources. This is especially true in arid regions where fresh water is limited. Desalination is a process that removes salt and other impurities from seawater. This makes it a valuable tool for increasing our freshwater supply. Desalination can help us to address the growing global water crisis. Reverse osmosis is like a sophisticated filter for water. Imagine a barrier with tiny holes so small that only water molecules can pass through. Salt and other impurities are left behind. This is the basic principle behind reverse osmosis. This process requires pressure to push the water through the membrane. Think of it like squeezing water through a very fine sieve. The result is clean, drinkable water on one side and concentrated salt water on the other. Reverse osmosis is used worldwide to provide fresh water for drinking, agriculture, and industry. It is a reliable and efficient way to combat water scarcity and ensure a sustainable water supply for the future. At the core of the reverse osmosis system is the membrane, a crucial component that determines the efficiency and effectiveness of the entire process. These membranes are often made of polyamide, a type of polymer, known for its strength and ability to filter out impurities. Polyamide membranes are designed to withstand high pressure and harsh conditions, making them ideal for industrial applications. Think of it as a very fine net that captures even the smallest particles. This net-like structure is what allows the membrane to effectively separate contaminants from water, ensuring that the output is clean and safe for use. However, even these robust membranes face challenges. Over time, they can become worn out and less effective. One of the main issues is fouling, where impurities build up and block the pores. This fouling can be caused by various factors, including organic matter, microorganisms, and mineral scaling. This reduces the flow of water and the efficiency of the desalination process. When the pores are clogged, the system has to work harder to push water through, leading to increased energy consumption and operational costs. To combat this, scientists are constantly looking for ways to improve polyamide membranes. Research is focused on developing new materials and coatings that can resist fouling and extend the lifespan of the membranes. One promising approach involves using chitosan, a natural polymer derived from shellfish, to enhance the performance and lifespan of these membranes. Chitosan has unique properties that make it an excellent candidate for this purpose, including its biocompatibility and ability to form strong, durable films. Chitosan is a natural polymer found in the shells of crabs, shrimp, and lobsters. It has unique properties that make it ideal for enhancing reverse osmosis membranes. Think of it as a natural booster for our water filtration system. When added to polyamide membranes, chitosan improves their ability to reject salt. This means that more fresh water can be produced with less energy. This is because chitosan helps to create a more uniform and selective membrane structure. The concentration of chitosan used is crucial. Too little, and the benefits are minimal. Too much, and it can clog the membrane. Finding the optimal concentration is key to maximizing both water flow and salt rejection. Section 5, the pressure is on optimizing water flow. In this section, we will delve into the intricacies of how pressure impacts the efficiency and effectiveness of reverse osmosis systems. Applied pressure is another critical factor in reverse osmosis. The pressure applied to the system plays a pivotal role in determining the rate at which water is filtered and purified. Higher pressure forces water through the membrane at a faster rate, increasing the volume of fresh water produced. This means that with the right amount of pressure, the efficiency of the system can be significantly enhanced. Think of it like squeezing a water bottle harder to make the water come out faster. The more force you apply, the quicker the water flows out. However, there is a trade-off. While higher pressure can increase the rate of water production, it also brings about certain challenges that need to be managed. While higher pressure increases water flux, it can also lead to membrane fouling. This fouling occurs when impurities in the water are forced into the tiny pores of the membrane. This is because the increased pressure can force impurities into the membrane pores, clogging them over time. As these pores become blocked, the efficiency of the system decreases. Finding the optimal pressure is a balancing act. It requires a careful balance between applying enough pressure to maximize water production and avoiding excessive pressure that could damage the membrane. It requires careful consideration of the membrane properties, the salinity of the feed water, and the desired water flux. By understanding these factors, technicians can optimize the system for the best performance. Gamma radiation, a type of high-energy electromagnetic radiation, can be used to further enhance the performance of chitosan-modified membranes. Think of it as giving the membrane a boost of energy to make it even more effective. Exposure to gamma radiation causes changes in the chitosan structure, making it even more effective at rejecting salt and other impurities. It's like giving the membrane a workout to make it stronger and more efficient. This treatment can also improve the membrane's resistance to fouling, further extending its lifespan. This means less frequent membrane replacements, reducing the overall cost of desalination. Another way to enhance reverse osmosis membranes is by incorporating titanium dioxide or TiO₂ nanoparticles. These nanoparticles have unique properties that make them incredibly useful in water purification. TiO₂ nanoparticles are photocatalytic, meaning they can use sunlight to break down organic pollutants. This helps to keep the membrane clean and prevents fouling. It's like having a self-cleaning membrane powered by the sun. Moreover, TiO₂ nanoparticles increase the hydrophilicity of the membrane, making it more water-loving. This allows water to pass through more easily, increasing the overall efficiency of the desalination process. The modifications discussed above offer significant improvements in reverse osmosis membrane performance. By incorporating chitosan, applying optimal pressure, utilizing gamma radiation, and embedding TiO₂ nanoparticles, we can create highly efficient and long-lasting desalination systems. These advancements translate into several key benefits. First, they enhance salt rejection, producing higher quality fresh water. Second, they improve water flux, producing more fresh water with less energy. Finally, they increase membrane lifespan, reducing the need for frequent replacements and lowering operating costs. The enhanced performance of these modified membranes has a direct impact on energy consumption. By utilizing advanced materials like polyamide and chitosan, these membranes are able to filter water more effectively and with less resistance. This means that less energy is required to push water through the system, leading to significant energy savings over time. With improved water flux and reduced fouling, desalination plants can operate more efficiently, requiring less energy to produce the same amount of fresh water. This efficiency is achieved through the membrane's ability to maintain high levels of water permeability, while effectively rejecting salts and other contaminants. As a result, the operational costs of desalination plants are reduced, making the process more economically viable. This energy saving is crucial for making desalination a more sustainable solution for our growing water needs. As global populations increase and freshwater resources become scarcer, the demand for efficient desalination technologies will only grow. By reducing the energy footprint of these processes, we can ensure that desalination remains a viable option for providing clean water to communities around the world. By reducing the carbon footprint of desalination, we can ensure access to clean water while minimizing our impact on the environment. This is achieved through the use of energy-efficient technologies and renewable energy sources, which help to lower greenhouse gas emissions associated with water production. In turn, this contributes to the global effort to combat climate change and protect our planet for future generations. The future of clean water relies on innovation and the development of advanced technologies like enhanced reverse osmosis membranes. Researchers and scientists are continually exploring new materials and methods to improve the efficiency and effectiveness of these systems. By investing in research and development, we can unlock new possibilities for sustainable water production. By continuously improving these technologies, we can move towards a future where clean water is abundant and accessible to all. This vision of a sustainable tomorrow is within our reach, but it requires a commitment to innovation, investment, and collaboration across industries and governments. Together, we can create a world where everyone has access to the clean water they need to thrive.
Today, we're excited to highlight groundbreaking research that addresses one of the most critical challenges of our time: water scarcity. The research we'll discuss focuses on advanced membranes for desalination, a vital step toward providing clean water to communities worldwide. This remarkable study is titled Surface Modification of Thin Film Composite Membranes using Gamma-irradiated Chitosan and TiO₂ for Enhanced Desalination Performance, and was published in the Desalination and Water Treatment Journal, Volume 160, 2019, pages 32 to 40. This pioneering research was carried out by a team of highly distinguished scientists. 1. Dr. Haney Gayed, lecturer at the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. 2. Assistant Professor Fatin Ismail Abu El Fadel, from the same department at NCRRT, Egyptian Atomic Energy Authority. 3. Professor Dr. Nabila Maziad, also from the Polymer Chemistry Department at NCRRT, Egyptian Atomic Energy Authority. 4. Professor Dr. Abdel Hamid El Assar, affiliated with the Egyptian Desalination Research Center of Excellence at the Desert Research Center, Cairo, Egypt. And 5. Professor Dr. Mohammed Sabri Abdel Motaleb from the Faculty of Science, Ain Shams University, Cairo, Egypt. This research explores the use of gamma-irradiated chitosan combined with nanoparticles of titanium dioxide to modify thin film composite membranes. These membranes were designed to enhance the efficiency of reverse osmosis systems, critical for desalination. By applying advanced techniques such as gamma irradiation, the team successfully developed a surface modification process that improves membrane performance, including salt rejection and water permeability. Their findings have the potential to revolutionize water treatment systems, making desalination more efficient and sustainable. We want to extend our deepest gratitude to the exceptional research team for their remarkable contribution to solving global water challenges. Your hard work and dedication are truly inspiring, and we're proud to share your work here on the For Science Salah Lotfy channel. To our loyal viewers, thank you so much for your continued support. We are truly grateful for your engagement and interest in the exciting topics we cover. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. Your support allows us to continue bringing you the latest scientific breakthroughs. Thank you for watching, and stay tuned for more fascinating discoveries here on For Science Salah Lotfy channel.